Imagine this. A silent traveller from another star system sliding past the edge of Mars, moving faster than storms, older than memory, and stranger than anything our instruments expected. Listener, you didn't arrive here by accident. Something in you, or in the universe, brought you to this moment, to this mystery. What are the odds that an object this massive, the largest interstellar visitor ever detected, would drift into our skies with a 1 in 500 chance trajectory, and a 60% rating for not natural? What if its glow, its chemistry, its silence are all trying to tell us something? Stay with me. Let's drift a little deeper. There are moments in astronomy when data behaves like a whisper. Not a declaration, not a revelation, but a shift so quiet and so subtle that only those who listen carefully can sense the tremor beneath the numbers. The arrival of 3I Atlas is one such moment. This object, drifting into the inner solar system from the deep galactic past, has forced astronomers to reconsider fundamentals, chemistry, probability, and even the assumptions that bind our models of natural cosmic behaviour. 3I Atlas is not simply another interstellar wanderer. It is the third confirmed object to enter our system from beyond the Sun's gravitational family, following Oumuamua in 2017 and Borisov in 2019. Yet from the moment of discovery, this visitor distinguished itself. Its brightness profile, chemical composition and trajectory collectively form a pattern of anomalies so persistent that scientists are left balancing skepticism with unease. Harvard astrophysicist Avi Loeb, known for challenging conventional interpretations of anomalous data, rated the object a 6 out of 10 on the scale of potential technological origin. It is not a claim, it is a probability, a 60% chance, neither certain nor dismissible, that 3I Atlas is not behaving like a natural comet. Loeb's rating was not based on speculation. It emerged from independent observations by NASA's James Webb Space Telescope, the Hubble Space Telescope, and the Very Large Telescope in Chile. Each instrument, using different wavelengths and methods, reported characteristics that diverge sharply from what comets normally exhibit. The first anomaly is chemical. Webb detected that 95% of 3I Atlas's gas plume consists of carbon dioxide and only 5% water. This ratio is 16 times more extreme than any known comet observed at comparable distances from the Sun. Solar system comets are water-rich remnants of icy reservoirs where water ice was stable during planetary formation. The CO2 dominant profile of 3I Atlas implies an origin in a radically different environment, perhaps a colder older system with distinct chemical gradients. It is a signature difficult to reconcile with familiar cometary behaviour. The second anomaly is even more profound. Spectroscopy from the Very Large Telescope revealed strong emission lines of nickel but no iron. In astrophysics, nickel and iron are inseparable twins. Formed together in the collapsing cores of massive stars and expelled into space through supernovas, these elements appear in predictable ratios across meteorites, asteroids, and comets. Detecting nickel without iron contradicts every model of cosmic chemical formation. The only context in which pure nickel is routinely separated from iron is industrial refinement, a process conducted by technological civilizations, not natural astrophysical environments. This discovery triggered immediate debate. Critics proposed that volatile nickel-carbonyl compounds could theoretically form in extremely cold interstellar regions and sublimate separately. Yet no evidence exists for such compounds on any previously studied comet. Even this explanation fails to account for the total absence of iron, whose carbonyl compounds should form under the same conditions. The simplest natural hypotheses have so far failed to survive scrutiny. Trajectory analysis added a new layer to the mystery. 3I Atlas travels on a retrograde path inclined at about 175 degrees to the ecliptic plane. Despite the retrograde motion, the path aligns almost perfectly with the flat disk containing the orbits of the planets, a 1 in 500 probability for a random interstellar object. It also executes close approaches to multiple planets, Mars in October 2025, Venus weeks later, and Jupiter in early 2026. Each individual encounter could be coincidental. but the sequence combined with the precise alignment raises statistical questions that natural explanations strain to answer. The amateur astronomy community added unexpected fuel to the discussion. During a lunar eclipse in September 2025, experienced astrophotographers captured images showing hard-edged structured forms beneath the comet's gas envelope shapes, inconsistent with a diffuse coma. Professional astronomers dismissed these images as artifacts or distortions caused by imperfect tracking. Yet these critiques were applied unevenly. When Hubble showed a forward-pointing glow, a feature impossible in standard comet physics, it was deemed anomalous but interesting. When amateurs observed similarly puzzling structures, those observations were discounted without replication attempts from larger telescopes. The forward-pointing glow itself deserves attention. In July 2025, Hubble captured a dust cocoon elongated toward the Sun, opposite the direction cometary tails should appear. Radiation pressure pushes dust away from the Sun, not toward it. Later observations showed a more traditional anti-solar tail. Something changed between July and August, or the viewing geometry obscured a phenomenon not yet understood. No model fully accounts for the combination of forward glow, delayed tail formation, and infrared point source readings from NASA's Spherex telescope, indicating unusually cold dust or a compact structure. The timeline deepens the importance of imminent observations. On October 3rd, Mars orbiting spacecraft, Mars Reconnaissance Orbiter, Mars Express, and Trace, gas orbiter, attempted to capture the highest resolution images ever taken of an interstellar object. If the nucleus of 3I Atlas measures 5 kilometers across or larger natural origin, theories become difficult to sustain. Interstellar space should contain a vast population of smaller bodies compared to giants. Finding such a massive visitor before cataloguing thousands of smaller ones contradicts expected size distributions. After October, the object slipped behind the Sun, hidden from all Earth-based telescopes for nearly 2 months. Its perihelion passage on October 30th, when cometary activity peaks and behaviour becomes most revealing, occurred entirely out of view. This concealment, whether natural or intentional, prevents scientists from observing the period when volatile chemistry fragmentation, or propulsion if any exists, would be most detectable. The object is expected to emerge again in early December. If it appears where gravitational models predict the natural explanation regains stability, if its trajectory has shifted without gravitational cause, then new possibilities must be considered, however uncomfortable. What remains certain is that 3I Atlas stands at a crossroads in scientific understanding. Whether natural or artificial, it challenges assumptions about formation chemical evolution and the statistical behaviour of interstellar visitors. It is a reminder that the universe still holds doors we have not opened, whose hinges we do not understand, and whose shadows stretch farther than our instruments can yet see. There are periods in the study of the sky when professional silence grows louder than the data itself, when anomalies accumulate faster than explanations, and those who stand outside the formal institutions become the first to notice patterns that official channels hesitate to acknowledge. The second stage of the 3I Atlas story begins with such a moment, quiet at first, almost accidental, but eventually impossible to ignore. While large observatories processed their spectral readings, amateur astronomers across the world turned their telescopes toward the strange green wanderer. These observers, often working alone under open skies, brought a different kind of scrutiny, a mixture of patience, persistence, and the intuitive sensitivity that comes from spending years simply watching. Their equipment is smaller, but their attention is sharper, unburdened by committee schedules or the need to defend a theory. On September 7th, during a total lunar eclipse, 2 respected amateur astrophotographers, Michael Yeager and Gerald Riemann, captured images that immediately stood out. In the strange dimmed light of the eclipse, 3I Atlas glowed green with a faint blue tinge along the edges. The object looked unusually structured, as if something beneath the gas envelope held shape contour or even geometry. Unlike typical comets that blur softly outward, this one appeared almost outlined. Professional astronomers confirmed the authenticity of these eclipse images, but they did not endorse the implications. The colour, the brightness, the crisp structure, they were acknowledged but not examined publicly. Then within days, more images appeared. Anonymous posts on astronomy forums, raw frames on Reddit, stacked exposures on Twitter. Different telescopes, different nights, different observers, yet the patterns were consistent. Hard edges, compact cores, irregular shapes that didn't match established models of cometary comas. Some photographs showed elongated structures pointing in unexpected directions. Others revealed concentrated brightness that suggested solid boundaries rather than diffuse dust. The reaction from the scientific establishment was swift but not investigative. Professional astronomers dismissed the images as exposure artifacts, motion blur and tracking errors. They warned that amateurs were misinterpreting faint objects glowing at magnitudes far below naked eye visibility. And yet the same professionals did not make corresponding efforts to replicate the observations with larger instruments. They did not request coordinated imaging sessions or compare technical parameters. The conversation remained one-sided critique without verification, dismissal, without investigation. The inconsistencies began to trouble independent analysts. The telescope that first discovered 3-eye Atlas, the Atlas survey instrument in Hawaii, has a 20-inch aperture comparable to high-end amateur telescopes. If a 20-inch survey instrument could detect the object's early form, then similar-sized hobbyist equipment should be capable of capturing meaningful structure as well. The argument that amateurs lacked sufficient optical power lost strength. What unsettled many was not the professional skepticism itself, but its uneven application. When Hubble captured a forward-facing glow, a phenomenon that violates basic comet physics, it was described as puzzling, noteworthy, and worthy of further study. But when amateurs captured anomalies from the same time period, the response was error, artifact, or misinterpretation. The contradiction suggested something deeper than disagreement. It hinted at discomfort. Indeed, the Hubble image from July 21st remains one of the most curious data points in the entire timeline. Instead of a tail streaming away from the Sun, as radiation pressure demands the bright region on 3-eye Atlas pointed toward the Sun. A forward coma, a glow moving opposite to every known physical mechanism. Even the most generous explanations tracking artifacts, dust density, anomalies scattering angles failed to match the image's structure. Yet the anomaly was treated as temporary, conveniently forgotten, when later images showed more typical tail formation. What changed between July and late August? The Gemini South Observatory captured new images that appeared more normal, showing a faint anti-solar tail. But this only complicates matters. If the forward glow was simply an artifact, why did it align so clearly with the object's motion? If it was real, why did it vanish so suddenly? Theories emerged about viewing angles, dust density thresholds, or delayed activation of sublimating ice. Yet none fully explained the timeline. As amateur and professional data began to diverge, another puzzle emerged from the infrared. NASA's Sphere-X telescope, which surveys the sky in thermal wavelengths, detected 3-eye Atlas as a point source, a dot. No extender coma, no long dust trail, no thermal halo. A comet actively ejecting material should shine brightly in infrared, its warming gases radiating heat. Instead, 3-eye Atlas appeared thermally compact, almost cold. That contradiction, visible extension but infrared compactness, remains unresolved. This period between July and early September forms a pattern of contradictions. A forward-facing glow that should not exist. A tail that forms weeks later without clear cause. Amateur images showing structure where none should be. Infrared readings showing a point source instead of an extended object. Spectral lines revealing chemistry unlike any natural comet. Individually, each anomaly can be debated. Together they create an uncomfortable mosaic that neither traditional comet models nor simple imaging errors can fully explain. Scientists occasionally remark that nature rarely produces single anomalies, it produces clusters. Thurbius Atlas appears to be such a cluster. The challenge is distinguishing between anomalies that expand scientific understanding and those that signal an incomplete or incorrect model. In the case of interstellar objects, of which only 3 have ever been observed, the models are thin, uncertain, and easily challenged. Amateur astronomers continued uploading images through September. Some were blurry, some were grainy, some were inconsistent. Yet among them were patterns, compact cores, asymmetric brightness, sharp gradients inside the gas envelope. The discussions grew intense. on forums threads stretched for hundreds of comments debating whether the structure was real or imagined natural or artificial, significant or irrelevant. The deeper issue lay not in the images themselves, but in what they represented: a widening gap between what the sky appeared to show and what the scientific establishment was willing to contemplate. The images became symbols of a larger uncertainty, a sign that the behaviour of Three-Eye Atlas defied easy categorization. In astronomy, uncertainty is not a flaw, it is a frontier. Yet uncertainty becomes uncomfortable when anomalies accumulate faster than explanations. The reluctance of the professional community to engage publicly with the amateur findings reflects a familiar tension, the desire to maintain caution in extraordinary claims without prematurely closing the door on genuine discoveries. The truth may lie somewhere between the skepticism and the intrigue. Maybe the structured images are partially distorted but partially real. Maybe the forward-facing glow has a natural explanation that has not yet been articulated. Or maybe the object's behaviour truly sits outside our expectations. Whatever the case, the period of July to September 2025 will remain the first chapter in a mystery that deepened rapidly. It was the moment when the sky stopped behaving like a textbook and started behaving like a question. And it was the moment when people across the world, professional and amateur alike, looked upward and felt the quiet strangeness of an object that refused to tell us what it was. In the story of Three-Eye Atlas, this was the beginning of collective doubt, the gentle, unsettling moment when observation surpassed explanation and the unknown stepped quietly into view. Every interstellar visitor enters the solar system on its own terms, following a path shaped by gravity chance and ancient momentum. But some trajectories feel too elegant, too precise, too improbably aligned to be dismissed as random. As Three-Eye Atlas approached Mars in early October 2025, astronomers began to notice that its movement was not simply unusual, it was exact. On October 3rd, the object passed 29 million kilometers from Mars. In cosmic terms, that distance is vast. In orbital mechanics, it is intimate. What intrigued scientists was not the distance itself, but how cleanly the object threaded its way through the orbital path of the red planet. The minimum orbit intersection distance the closest the object would ever come to Mars's complete orbital track was just 2.7 million kilometers. To planetary dynamicists, that number was startling. Avi Loeb called it remarkable fine-tuning, a phrase that carries scientific weight and philosophical tension. Fine-tuning suggests precision deliberation, or at the very least a statistical outlier that demands attention. Natural comets wander, they drift. They are perturbed, fragmented, pulled and scattered. But Three-Eye Atlas seemed to be following a corridor through the solar system as if aware of its architecture. This encounter became one of the most anticipated astronomical events of the decade, not because Mars posed danger, but because it offered something far rarer, a brief moment in which spacecraft orbiting another world could attempt to image an interstellar object at unprecedented resolution. The Mars Reconnaissance Orbiter, circling the planet since 2006, possesses the HiRISE camera, an instrument capable of capturing details as small as 30 centimeters from Martian orbit. When pointed at a distant object millions of kilometers away, the resolution drops to about 30 kilometers per pixel. But even this was enough to distinguish between a small compact nucleus and a larger structure. It was enough to confirm whether the brightness surrounding Three-Eye Atlas was dust, ice, rock, metal, or something entirely unexpected. The uncertainty was exhilarating. If HiRISE detected a nucleus 5 kilometers wide, the size implied by mass calculations, then natural comet theory would bend under the strain. Interstellar space should host countless small objects. Before discovering a giant, we should have detected tens of thousands of smaller wanderers. Discovering a 5-kilometer interstellar object this early in humanity's observational era defied probability. Yet size was only one question among many. Another possibility hovered quietly at the edges of scientific conversation: the presence of additional objects. Some scenario models suggested that if Three-Eye Atlas were technological, it might deploy precursor probes, smaller bodies sent ahead to survey individual planets. One such probe, travelling tens of millions of kilometers ahead of the primary object, could intersect the orbit of Mars in early October without detection. At that distance, Earth's telescopes cannot see objects smaller than roughly 100 meters. Every spacecraft humanity has ever launched falls below that threshold. This fact alone made the Mars encounter more than an imaging opportunity. It became a test of the impossible, a moment when the solar system might reveal multiple moving bodies where only one was expected. A natural comet cannot eject a shard or fragment at the necessary velocity to redirect toward a planet. Sublimation-driven jets produce speeds far below the required tens of kilometers per second, but a technological object equipped with propulsion could make such a maneuver trivially. This was not the mainstream interpretation. It was not the conclusion taught in university classrooms, yet the mathematics left an open door. A door no astronomer could fully close without data. Mars Express and the ExoMars Trace Gas Orbiter joined the observation campaign, turning their spectrometers and cameras toward the approaching visitor. These spacecraft normally study the Martian surface atmosphere and mineralogy, yet for this brief moment they were reassigned to something unprecedented, the characterization of an interstellar body from another world. Their instruments could measure the chemical lines in the gas surrounding 3I Atlas, analysing carbon monoxide, cyanide, carbon dioxide and other volatiles at distances no ground-based telescope could duplicate. They could detect fluctuations in brightness, hints of fragmentation, or spectral signatures that natural comets should not produce. But these spacecraft had another quieter purpose: to scan the space around the object, not just the object itself. If something was travelling ahead of 3I Atlas, only these orbiters could see it. Avi Loeb had specifically proposed this idea use high-rise not simply to photograph the main body, but to search for companions. NASA's public statements avoided such speculation. Agencies choose caution over conjecture. But within private mailing lists and corridors of astrophysics conferences, the idea circulated quietly. If a precursor probe existed, this encounter was the only chance to detect it. The timing added an eerie symmetry to the mystery. The Mars flyby happened precisely 1 week before 3. Atlas vanished behind the Sun from Earth's perspective. The geometry of the solar system would place the object in total solar glare for 2 months. During that time, no telescope on Earth could see it. No observatory could track its motion. No camera could detect anomalies. The visitor would move silently, hidden behind 150 million kilometers of incandescent plasma. If something required discretio, if maneuvers, deployments or adjustments were to occur, this was the perfect window. Naturalists offered explanations rooted in physics. The object might fragment. Comets commonly crack under perihelion heating. Sublimation could increase dramatically, creating jets that cause rotational changes. Such behaviour is normal, documented, predictable. But those same natural arguments acknowledge something else. Any fragmentation during these 2 months would be invisible. We would only see the aftermath after the object emerged again in December. What would look like a debris field to some might look like deliberate deployment to others. The uncertainty was inevitable. Observers prepared for the December reappearance with a mix of anticipation and anxiety. Telescopes were scheduled weeks in advance. Some astronomers privately confessed to colleagues that they feared nothing more than a trajectory deviation, not because of danger, but because of implication. If 3 Atlas emerged from behind the Sun in a position inconsistent with gravitational prediction, the scientific world would face a moment it had never prepared for. One astronomer described it as the line we cannot uncross. For now, the Mars encounter stands as a turning point, a moment when speculation gained structure, when probabilities condensed into questions that instruments might finally answer. Whether the data reveals a natural relic from an ancient star system, or the first evidence of something engineered, is almost secondary. The true significance lies in the shift itself. Before 3 Atlas, interstellar objects were curiosities. After 3 Atlas, they became invitations, subtle reminders that the universe is older, stranger, and more deliberate than we once believed. In this way, the October encounter was not just a scientific event. It was a moment of human introspection, a rare instance when the cosmos presented us with a mirror, instead of a map reflecting our readiness or unpreparedness to meet whatever moves through the dark between stars. Some mysteries do not arrive loudly. They reveal themselves the way a distant star brightens through a telescope lens quietly, steadily demanding your attention long before you realise why. The mystery of Three-Eye Atlas deepened in precisely this way, not through dramatic motion or sudden bursts of light, but through the delicate fingerprints of its chemistry. Traveller, listen closely. Chemistry is the universe's handwriting. Every atom, every molecule, every spectral line is a sentence written across billions of years. And in late July and August of 2025, one telescope after another began reading a sentence that should not exist. The Very Large Telescope in Chile, one of Earth's most precise eyes, detected something astonishing. From the gas plume surrounding Three-Eye Atlas, strong and unmistakable emission lines of neutral nickel streamed outward into space. The lines were sharp, clean, and bright enough to be undeniable. But accompanying them was something more unsettling than the discovery itself. There was no iron at all. In nature, nickel and iron are inseparable twins. They are forged together in the fiery cores of dying stars and cast outward in supernova explosions as bonded elements. Every meteorite, asteroid, and comet humanity has ever studied carries both in fixed proportions. To find nickel without iron would be like discovering a river with no water, a flame with no heat. It violates the cosmic rules we trust without question. And yet, Three-Eye Atlas violated them effortlessly. Scientists reached for explanations, but the explanations reached back like shadows, thin, fragile, and uneasy. Some suggested that nickel-carbonyl compounds might form in the extreme cold of interstellar space. These molecules could in theory break apart under sunlight and release pure nickel. A scientific possibility, yes, but a possibility never observed, never confirmed, never even hinted at in the long catalogue of known comets. Others argued for statistical anomalies or unknown chemistry. But beneath their caution was something quieter, something almost fearful. These explanations were too convenient, too improvised, too eager to fill the silence. Because the simplest explanation, the one nature never offers but humans hesitate to speak aloud, was that the signature resembled industrial processing, not cosmic formation. On Earth, high-purity nickel is separated from iron deliberately through smelting, refining, and chemical engineering. Its uses are specialized aerospace alloys, electronics, magnetic components. It is the metallurgy of purpose, not accident. And then another layer unfolded. When first detected in July, the nickel emission was modest. A signal, yes, but a gentle one. By late August, it had increased 25-fold, a surge so steep it resembled engineered scaling more than natural sublimation. The closer Three-Eye Atlas drifted toward the sun, the more nickel it released, as if something on its surface were being systematically vaporized. The easy explanation, country activity, falters in the details. Natural outgassing increases gradually as solar heating intensifies. But the nickel spike from Three-Eye Atlas was not gradual. It was exponential, a curve far too steep to match standard models. Skeptics pushed back. Jason Wright called Loeb's interpretation misleading. Others insisted the signature must have a natural cause simply because natural causes are safer to believe. But in quiet corners of observatories, in late-night email threads between researchers who preferred caution over publicity, the same question whispered itself, over and over, where is the iron? Because iron, unlike nickel, forms similar volatile compounds. If nickel carbonyls survive interstellar travel, iron carbonyls should too. But the spectrum remained silent. No iron lines, not even a trace. Silence in science is often more terrifying than noise. As weeks passed, more data emerged. The Very Large Telescope detected surging hydrogen cyanide, another compound increasing at an abnormal rate. Cyanide is not unusual in comets, but the acceleration was. It suggested a linkage with the nickel release, as if multiple chemical processes were being driven by the same hidden cause. Even amateur astronomers noticed something uncanny: the object's colour changed. In July, the Three-Eye Atlas glowed faintly red, typical, even comforting for a comet rich in organic dust. By early September, it shone bright green, illuminated by molecules that amateur telescopes could detect, but professional models struggled to explain. Yet Three-Eye Atlas had previously shown extremely low levels of the very carbon molecules that produce green emission. Traveller imagined watching a stone change colour under moonlight, not through gentle heating, but overnight, as if reacting to something unseen. Some astronomers speculated about a cooked shell, shaped by billions of years in interstellar cold. Others spoke of extreme processing by cosmic rays, but even these explanations felt stretched, like trying to cover a growing wound with a thinning bandage. The question deepened: if this object truly originated around another star 11 billion years ago, how much could time itself alter? How much could radiation reshape? Yet even the most generous models could not reconcile the absence of iron. The mystery grew heavier when NASA's SPHEREX telescope entered the conversation. SPHEREX saw Three-Eye Atlas not as a cloud, not as a diffuse plume of dust, but as a point source, a compact, concentrated, radiating body. Infrared telescopes cut through dust, revealing the warmth beneath. If the object was spewing dust and ice freely, SPHEREX should have seen an extended glow. It did not. The universe, it seemed, was tightening the circle. Every observation removed a familiar explanation and left behind something too dense, too massive, too chemically strange to fit what we know. As the sun drew closer on its path, the object continued its silent transformation. Observatories worldwide held their breath, waited for new spectra, new curves, new answers. But for every answer, another question appeared. And through it all, one quiet truth lingered, somewhere in the cold dark between stars. Atlas had been shaped by conditions we do not yet understand, or by intentions we have not yet dared to imagine. Whether natural or not, whether ancient debris or engineered relic, it forced us to confront the limits of our models, the narrowness of our assumptions, and the delicate line between science and wonder. And somewhere beneath the data, beneath the emission lines, and probabilities, a softer realization formed. Some mysteries aren't meant to be solved, only observed, only respected, only approached with humility under the silent sky. There are times when the universe behaves in ways that feel intentional, as if celestial mechanics are arranging themselves into a narrative too precise to be accidental. The disappearance of Three-Eye Atlas behind the sun in late September became one of those moments, not because the object was lost or destroyed, but because it entered a region of space that made observation impossible at the exact moment when observation mattered most. Its timing transformed a simple orbital alignment into a scientific enigma. The geometry of the event was straightforward Earth-the-Sun, and the interstellar visitor formed a configuration that blinded every telescope on the planet. The most important phase of the object's journey, the approach to perihelion, on October 30th would occur entirely behind the solar disk. This was the moment when comets reveal their nature, when thermal stress exposes their structure, when spectrographic signatures peak. It was the moment astronomers needed most, and it was the one moment they were not allowed to see. For natural objects, coincidences happen without intent. Orbital paths intersect. Bodies drift in and out of view. But even traditionally minded scientists admitted privately that the timing felt unnervingly exact. Perihelion is the point at which any unusual chemistry outgassing pattern or fragmentation event would be most visible. Yet Three-Eye Atlas became invisible during the entire window of maximum scientific value. The alignment did not merely reduce visibility, it erased it. This absence forced researchers to rely on spacecraft positioned elsewhere in the solar system. The Parker solar probe skimming the outskirts of the sun's corona offered a faint hope of detection if its trajectory happened to align with the object's path. The SOHO observatory permanently watching the sun might catch a small silhouette drifting through its coronagraph images, though such instruments were never built for the delicacy of cometary science. JUICE, orbiting in the outer solar system, could theoretically gather data, but its antenna had been turned away to shield itself from intense radiation. The few tools capable of seeing through the glare were either poorly aligned, poorly positioned, or temporarily blind themselves. These limitations created a strange scientific silence. For 2 months, humanity would know nothing about the object's behaviour. It could fragment, accelerate, decelerate, or even alter its trajectory, and no one on Earth would witness any of it. When a natural comet behaves unpredictably, astronomers attribute it to thermal forces, structural weaknesses, or rotational stress. But when an interstellar object with anomalous chemistry and unprecedented mass does something unseen over a critical period, the absence of data becomes more provocative than the data itself. Speculation inevitably expanded. If the visitor was entirely natural, its behaviour behind the sun would follow predictable cometary patterns, heating, venting, expanding, possibly cracking, under pressure. But one scenario lingered with quiet persistence, the possibility that the object could use the hidden window to perform a manoeuvre, reducing velocity enough to slip into a bound orbit around the sun. A natural comet lacks the energy to make such a correction. A technological object, even a primitive one, would require only a modest impulse. These ideas found no official endorsement, yet they also found no satisfying rebuttal. The observational blackout became a philosophical puzzle as much as a scientific one. Could a coincidence this precise still be considered chance? Or was chance itself too fragile a framework to describe an interstellar visitor that had already broken so many expectations? As December approached, anticipation turned into a kind of global stillness. Telescopes around the world were booked for the reappearance window. Large observatories prepared high-resolution instruments, and amateur astronomers polished mirrors and calibrated mounts for what many saw as the most significant reacquisition effort in decades. The question at the centre of this effort was simple and profound. Would 3i Atlas return on the trajectory predicted by gravity? A natural object obeys gravitational law with unwavering fidelity. Deviations, aside from small outgassing effects, are minuscule and predictable. If the visitor reappeared exactly where celestial mechanics modelled it, the natural explanation would regain its footing. But any deviation, any shift too large to be explained by sublimation, would mean only one thing: propulsion. Trajectory, after all, is the most honest language in the universe. This expectation created a subtle tension in the scientific community. Observatories prepared collaborative campaigns. Astronomers discussed protocols privately acknowledging that an unexpected outcome would require immediate coordinated interpretation. Some even debated how such discovery should be communicated to the public. The procedures for detecting alien radio signals exist. The procedures for detecting alien objects do not. Fragmentation too lingered as a double-edged possibility. If the object emerged in multiple pieces, naturalists could argue thermal breakup. But controlled or symmetric fragmentation, the kind that implies deployment rather than destruction, would carry different implications altogether. The ambiguity of unseen events transformed the disappearance into a scientific Rorschach test. Observers saw in it whatever their training, intuition or fear allowed. What made the entire situation feel almost poetic was the silent metaphor at its centre. A visitor from another star system approached the sun, underwent its most transformative moment in total invisibility, and then prepared to re-emerge into view. The scientists waiting on Earth were not merely gathering data, they were waiting for revelation, as if the object carried a message written in heat, gravity and silence. And so the disappearance behind the sun became more than an observational barrier. It became an intermission authored by the cosmos, a moment in which human curiosity was forced into stillness, a moment when the universe whispered, "Not yet, wait." In that waiting, something shifted. Scientists, observers and dreamers alike realized that the absence of information can be as profound as its presence. The universe teaches patience not through explanations, but through the quiet intervals in which all we can do is watch the sky and admit how little we understand. And when 3i Atlas finally emerged again in December, it would not simply be a continuation of its journey. It would be an answer one shaped by everything that happened in the months we were not allowed to see. An answer carrying perhaps the quiet message that some mysteries deepen, not in light, but in shadow. The mass of an object often tells its story more honestly than its light. In astronomy, weight is a confession. It reveals the density, the structure, the forces shaping an object's long journey through space. And when scientists calculated the mass of 3i Atlas, they encountered a number so large, so disproportionate to expectation, that it immediately unsettled the narrative surrounding this visitor. They began with motion. Comets, when heated by the sun, release gas like the slow exhale of ancient ice. This outgassing acts as a natural propulsion system, nudging the nucleus in measurable ways. These nudges are small but unmistakable. They leave signatures in the trajectory that astronomers can detect with ease. Yet 3 Atlas displayed almost none of them. Even as it lost enormous amounts of carbon dioxide, water and carbon monoxide, its path remained calm, steady, almost indifferent. The absence of non-gravitational acceleration became the first clue something was resisting the push of its own escaping gases. The only reasonable conclusion was mass, vast amounts of it. From more than 4,000 observations, the calculations converged at least 33 billion tons, a weight so immense that it dwarfed both previous interstellar visitors Oumuamua and Borisov by orders of magnitude. It suggested a nucleus 5 kilometers wide, a size that felt strangely deliberate, in a universe where small debris vastly outnumbers giants. This was where probability began to strain. If interstellar space ejects fragments at random, humanity should discover thousands of smaller objects, first not a behemoth. Yet the cosmos had delivered a heavyweight before delivering its pebbles, a sequence that made some astronomers uneasy and others quietly philosophical. Some proposed the brightness was misleading. Perhaps a cloud of dust surrounded the nucleus, masking its true size. But infrared data revealed no such halo. Spherics saw a point source, compact and undiffused, as if the core stood exposed rather than cloaked. Others suggested the object was a loose rubble pile held together by weak gravity. But rubble cannot withstand violent outgassing. If 3I Atlas were fragile, it should have shattered under its own activity. Instead, it remained intact, stable, almost stubbornly coherent. Mass is a truth that refuses to be explained away. The object's trajectory added another layer of complexity. When its motion was traced backward, it pointed toward the thick disk of the Milky Way, a region filled with ancient stars. If the object originated there, it could be older than Earth, older than the Sun, older than the modern spiral shape of our galaxy. Age alone might explain certain chemical scars, but it could not explain integrity. Large icy bodies do not typically survive billions of years without fragmentation. Why then was this one still whole? A few scientists quietly acknowledged an interpretation they would not publish. If a structure were built rather than formed, its mass might be intentional. Durability might be intentional. Its resistance to outgassing might be intentional. But the scientific community prefers silence over premature speculation. So attention turned to the October 3rd encounter with Mars. Instruments like HiRISE could refine size estimates, verifying whether the 5-kilometer nucleus was real or inflated. A smaller mass would relax the tension. A confirmed giant would deepen it. Yet before such measurements could anchor the debate, 3 Atlas vanished behind the sun, taking the rest of its secrets into a corridor of light where human instruments could not follow. And despite the caution, despite the insistence on natural explanations, the underlying question refused to dissolve. How does something so massive, so improbable, so statistically out of place arrive in our solar system at precisely this moment in our observational history? Some astronomers pointed to detection bias, the idea that our telescopes are finally good enough to notice these giants. But detection bias explains faintness, not rarity. It explains sensitivity, not improbability. Technology can sharpen our eyes, but it cannot rewrite the underlying distribution of matter in interstellar space. The mass of 3I Atlas therefore became more than a scientific challenge. It became a symbol of an unanticipated gravitational weight pulling at the edges of human understanding. It reminded researchers that nature is capable of producing surprises far beyond standard models, yet it also forced them to confront an uncomfortable truth: not every anomaly can be soothed with familiar explanations. Whatever 3 Atlas's natural relic or engineered wanderer, it moves with the authority of something built to endure time itself. Its weight is not merely physical, it is conceptual. It bends assumptions, it reshapes probabilities. It whispers that our models of the interstellar medium might be incomplete, or that our perspective on what wanders between stars might need to widen. And so the mass that should not exist remains for now an unanswered question drifting through a sky too vast for certainty. A reminder that the universe does not owe us simplicity, only wonder. Every comet carries a chemical memory and imprint of the place where it formed and the conditions it has endured. In most cases, that memory is predictable, following patterns etched into the universe since the earliest epochs of star formation. But 3C Atlas defied that predictability. Its chemistry did not reveal a place. It revealed a contradiction. The first indication came from the James Webb Space Telescope, whose instruments recorded a plume that was overwhelmingly carbon dioxide 95%, with only a faint trace of water. This inversion was not merely unusual, it was unprecedented. Water is the foundational volatile of nearly every comet we have ever observed. CO2 is typically secondary, a supporting actor rather than the lead, yet here it dominated the spectrum, rising like a voice that did not belong to any cometary lineage we recognised. Such a composition suggested a birthplace far colder than anything in our solar system, a region where temperatures suppress water into deep silence and allow carbon dioxide to take its place. It pointed toward a world not just distant but alien in the deepest chemical sense. Then came the colour shift. Amateur astronomers first described a reddish hue, the familiar glow of carbon-rich dust scattering sunlight. But during a lunar eclipse in early September, the object blazed bright green, edged with a thin blue halo. Green comets exist, but their colour comes from diatomic carbon, a molecule that 3I Atlas had previously been shown to lack. The very substance needed to produce the colour had been measured at abnormally low levels only weeks before. The transformation felt abrupt, almost reactive. Something had changed, not slowly, not by gradual warming, but suddenly and in harmony with a surge in other compounds. The surge in cyanide was the next puzzle. Hydrogen cyanide is common in comets, but its production rarely spikes so quickly. In 3I Atlas, it climbed in step with the nickel emissions mirroring the same exponential curve. It was as if separate chemical systems were responding to a single hidden trigger, each accelerating with eerie synchronization. Scientists looked for natural sequences that could explain such coordination. They found possibilities, but none of them rested on comfortable ground. Each explanation required an exception. Each exception required another. The puzzle remained intact, and then Spherex offered a perspective that further complicated the picture. While visible light observations showed a growing coma, the infrared data revealed none of it. No extended glow, no thermal emission from dust, only a sharp, compact infrared source, as if the warmth radiated from a hard surface rather than a diffuse cloud. This meant one of two things. Either the dust was extraordinarily cold, so cold that it absorbed almost none of the sun's heat, or its reflective properties were unlike anything observed in natural cometary material. Both possibilities strained conventional models. Astronomers turned toward origin as a potential explanation. Simulations traced 3I Atlas back to the thick disk of the Milky Way, a population of ancient stars formed during the galaxy's earliest and most turbulent era. A birthplace there might account for unusual chemistry, low metallicity, or extreme volatility ratios. But even an ancient origin could not explain everything. It could not explain the absence of iron when nickel was present. It could not explain the abrupt colour shift without the molecules that caused such emissions. It could not explain the mismatched signatures across different wavelengths. Piece by piece, the contradictions accumulated. Some researchers proposed the idea of a processed shell, surface altered by billions of years of cosmic radiation, dust impacts and temperature extremes. But while age can sculpt ice fracture bonds and reshape molecular layers, it cannot separate nickel from iron so cleanly, nor synchronize chemical surges across unrelated compounds. A deeper uncertainty began to settle over the scientific landscape. Not a belief that the object was artificial, but a recognition that the frameworks used to interpret comets were inadequate here. Nature can be strange, but its strangeness usually follows a logic. With 3D Atlas, the logic fractured. As more data accumulated, scientists realized that the anomalies were not isolated, they were sequenced. First the CO2 dominance, then the nickel spike, then the cyanide rise, then the colour shift, then the collapse of infrared dust signatures. A chain reaction, unfolding with unnerving rhythm. The pattern did not resemble the thermal evolution of a comet. It resembled a system-changing state. This realization did not produce answers, only more refined questions. What mechanism could orchestrate these changes? What conditions could produce such a blend of volatility and coherence? What history could shape a body that disregards so many natural rules? In that uncertainty, some observers felt a quiet philosophical unease. Science prefers either consistency or chaos, either predictable laws or stochastic variation. Thrusitkawasa's atlas offered neither. It offered patterns without causes, signals without context, transformations without precedent. It became a reminder that the universe contains processes we have not yet imagined and materials we have not yet catalogued. A reminder that anomalies are not threats to science, but invitations. As the object drifted closer to the sun, its chemical contradictions felt less like errors in our models, and more like messages, not in the sense of communication, but in the sense that reality itself was telling us to widen our assumptions. Perhaps these anomalies were simply the signature of an ancient comet from a region humanity has never studied. Or perhaps they represented something more extraordinary, a phenomenon shaped by conditions not present in our solar system, or shaped by intentions rather than accidents. But the essay must end with honesty we do not know. Not yet. What we do know is this three-eye atlas did not merely break rules of comet chemistry. It moved through those rules as if unaware they existed, leaving researchers with an object that obeyed no familiar category. And in that disobedience, it invited a deeper understanding not only of itself, but of the cosmos that shaped it, and the humility required to confront mysteries that exceed our expectations. In astronomy, some mysteries arrive quietly. They do not roar into view or announce themselves with spectacle. They reveal their strangeness through details, small deviations, gentle contradictions, fragments of behaviour that do not match the rules we expect. For Three-Eye Atlas, one of those contradictions appeared in the shape of its tail. When the Hubble Space Telescope captured the object on July 21st, something immediately felt incorrect. The glow surrounding the nucleus, a teardrop of dust and ice, was not trailing behind the object. It was pointing forward toward the sun. Comet tails simply do not behave that way. Radiation pressure and the solar wind always push material away from the sun, shaping the familiar backward sweep that has accompanied comets since the beginning of human observation. Yet here was a visitor, whose brightest side faced the very star that should have been pushing it away. The explanation at first seemed to lie in instrumentation. Hubble tracks objects as they move, allowing background stars to blur slightly. Some suggested the forward glow was a tracking artifact, a smear caused by the object's rapid motion. But the smear of stars was visible distinct linear. The forward-facing glow was not a streak. It was a region of concentrated brightness, structured and intentional looking, as though something about the dust cloud resisted the normal direction of solar forces. It was a quiet violation of elementary comet physics. Weeks later, Gemini South captured new images. Suddenly a more traditional tail appeared stretching behind the object in the expected anti-solar direction. Critics quickly seized on that, declaring the earlier anomaly solved. But the shift did not erase the puzzle, it sharpened it. Something had changed between late July and late August. Either the object had begun behaving like a normal comet, or the geometry of observation had shifted in exactly the right way to hide a tail earlier. Neither explanation sat comfortably. If the object simply hadn't developed a tail yet in July, why was the forward glow present at all? Why was it shaped rather than diffuse? And if the viewing angle had masked the tail, why did the brightness point toward the sun rather than remain symmetrical? These questions lingered even as new details emerged. The dust surrounding the object was measured to extend thousands of kilometers from the nucleus, with density decreasing by an immense factor as distance increased. Yet the glow at the outer edges remained detectable. That meant either an extraordinary volume of dust was being produced, or the particles were unusually reflective, reflecting sunlight, with an efficiency not typical of cometary grains. Simultaneously, different wavelength filters showed different shapes. In ultraviolet, the coma looked compact. In the red and infrared, it appeared more extended. This indicated that particles of different sizes were present, small grains, scattering blue light close to the nucleus, larger grains drifting farther out. These variations normally support a natural origin, but the forward glow still resisted explanation. Dust dynamics offered some possibilities. If particles were extremely small, sub-micron in size radiation pressure could accelerate them forward before gravity redirected them. But such forward acceleration would create a forward tail, not a compact glow, and the observed morphology did not resemble a tail at all. It resembled a halo pushed against the sun like a bubble resisting heat. Electrostatic charging was another consideration. Cometary dust can become electrically charged under intense ultraviolet radiation, interacting with the sun's magnetic field. Charged particles behave differently from neutral dust. They can be confined, repelled, or even sculpted into unexpected shapes. But even this hypothesis fell short. The structures Hubble detected were too orderly, too coherent. Meanwhile, other instruments added their own pieces to the puzzle. Sphere-X observed the object as a point source in infrared, no extended emission at all. If dust was present, it should have warmed and radiated infrared light. Instead, the instrument saw only the compact nucleus, as if the dust cloud did not exist in thermal wavelengths. To reconcile visible structure with infrared absence, the dust would have to be extraordinarily reflective or extraordinarily cold, colder than expected at that distance from the sun. That level of reflectivity would require materials uncommon in natural comets, and dust does not typically remain cold while being blasted by solar radiation. Each thread unravelled into another contradiction. Astronomers hoped that the approach toward the sun would clarify things. As the object heated, sublimation would increase, creating a clearer tail and revealing how dust and gas behaved under stronger solar forces. If the tail began behaving normally, pointing away from the sun, the July anomaly could be dismissed as an early-stage irregularity. But this shift created its own unease. When an object begins by breaking rules and later follows them, the question becomes not what it is, but why the transition occurred. Was the tail developing naturally, or was something changing? There was beneath the scientific discussion a quiet undercurrent of curiosity that bordered on mythic. The idea of a tail that pointed the wrong way carried an almost symbolic quality, as if the universe were reminding observers that certainty is temporary. A reminder that even well-understood forces like solar radiation and dust dynamics can be humbled by one unexpected traveller. And perhaps that was the heart of the matter. The forward glow was not just a scientific anomaly, it was a philosophical interruption. A moment in which familiar laws bent just enough to introduce doubt, not enough to provide answers. The tail that should not have existed, at least not in that orientation, became a kind of cosmic metaphor. Something moving against expectation. Something resisting the ordinary push of forces that shape everything else. Something that refused to behave like the objects we know. As 3i Atlas approached perihelion behind the sun, scientists were left with the lingering question: was this anomaly a glitch of perspective, or a truth about the object itself? They would not know until December, when it re-emerged from the solar glare, changed or unchanged, ordinary or extraordinary. The forward glow remained suspended in memory, a quiet riddle carved in light. A reminder once again that the sky is not a solved equation but a living manuscript, and sometimes a visitor arrives to write a sentence in a dialect we do not yet understand. Trajectory is the most honest language in the universe. Light can deceive, chemistry can complicate, dust can obscure. But motion, the path carved through space, rarely lies. It reflects the forces acting upon an object, the history embedded in its momentum, the quiet truth of where it came from and where it is going. For 3i Atlas, that path was the first whisper of something unusual. When astronomers calculated its orbit, they found that the object entered our solar system almost perfectly aligned with the ecliptic plane, the thin sheet of space where Earth, Mars, Venus and Jupiter circle the Sun. But it did not move in the same direction as the planets. It came against the flow retrograde threading through the architecture of our system, with a precision that felt oddly intentional. This geometry should be rare. Interstellar objects should arrive from random orientations scattered across the three-dimensional sky. Yet 3i Atlas approached along the plane of the planets with only a 5-degree deviation. The probability of this happening by chance was calculated at roughly 1 in 500. A number small enough to be dismissed but large enough to linger. The alignment wasn't the only curiosity. The object's path brought it near multiple planets. Mars first, then Venus, and in 2026 Jupiter. None of these encounters posed a danger. The distances were safe, millions of kilometers wide. But the pattern was strange. A natural interstellar object should sweep through the solar system with indifference. It should enter pass near the Sun and depart often without approaching any planets at all. 3 Atlas behaved differently. It moved as if tracing a route through points of interest. Scientists debated the implications. Some leaned on detection bias, arguing that we only see interstellar objects that happen to cross the inner solar system, and those that cross the inner solar system are more likely to align with the ecliptic. But bias alone could not explain the combination of alignment encounters and timing. It was the timing that unsettled many. The object entered the inner solar system in mid-2025, just as the new Vera Rubin Observatory became operational, just as the Atlas survey reached full cadence, just as Spherex and other instruments began scanning the sky with unprecedented sensitivity. It appeared at the exact historical moment when humanity gained the ability to study such an object in detail. Coincidence is part of science, but coincidence layered upon coincidence becomes a structure. Some astronomers suggested that the orbit might be shaped by past interactions. Perhaps the object had long ago encountered another star altering its direction, but simulations contradicted this. The path traced backward into the Milky Way's thick disk, consistent with a stable, undisturbed trajectory travelling for millions of years. Nothing obvious had sculpted its alignment. Nothing gravitational, nothing chaotic. It simply arrived this way. The eccentricity of its orbit added another dimension. At 6:16, it was far beyond the threshold for escape velocity. This was not a returning comet. It was a visitor entering, passing, leaving. Yet the speed at which it approached our system matched the expected velocities of ancient objects from the thick disk. Natural in speed, uncanny in angle. As scientists examined these details more closely, they realized something subtle. The trajectory was not merely rare, it was efficient. It positioned the object to pass near the planets most studied by automated spacecraft. It aligned it with instruments already orbiting Mars and soon orbiting Jupiter. It offered opportunities for observation, as if by design, not by chance. No one claimed design openly. But no one ignored the symmetry either. The simplest possibility remained that the universe, vast and unpredictable, had delivered a rare but natural configuration. And perhaps that was enough. Rare events occur, unlikely alignments arise. Our solar system, like every other, is full of improbable histories. Yet one uneasy question lingered: if this were random, why did the path resemble a survey? A survey trajectory would need to cross the ecliptic plane pass near major planets and approach the Sun without falling into collision. It would need to maintain high speed consistent with interstellar travel while still allowing proximity to points of interest. And it would need to approach at a time when a civilization could observe it. A natural body can match these conditions by accident, but matching them all at once, geometry, timing, planetary encounters, observability stretches coincidence into something that resembles choreography. Some researchers proposed a different perspective. Perhaps the trajectory was not deliberate but opportunistic. Perhaps we are the ones interpreting it backward, imagining intention, simply because the alignment benefits us. The human mind is skilled at recognizing patterns, especially when those patterns feel personal. Yet even this humility did not resolve the unease. The object's behavior near Mars intensified the debate. The minimum orbit intersection, distance only 2.7 million kilometers, was described by Xavier Loeb as remarkably fine-tuned. Not dangerously close, but precise enough to suggest that even a small velocity adjustment could create an encounter. A natural comet cannot make such adjustments. Outgassing produces too little thrust to alter an interstellar trajectory meaningfully. But even a minimal propulsion system could. And that was the quiet implication no one wanted to name. The possibility was not that the object was a spacecraft. The possibility was simpler, subtler, that its trajectory was not purely gravitational, that somewhere in its distant past a small correction had nudged it onto a path that would eventually lead here. A correction so tiny it left no obvious trace. A correction so ancient its purpose was forgotten. A correction that, like a seed planted in a deep time, bore fruit only now. This hypothesis was not accepted, but neither was it dismissed, because the object continued to defy expectations in ways too consistent to ignore. And so the trajectory of 3i Atlas became a mirror reflecting not only the nature of the object, but the assumptions of the observers. Was this path random or meaningful? Was the alignment cosmic coincidence or quiet intention? Was the timing arbitrary or synchronistic? The universe does not answer these questions directly. It only offers motion and leaves interpretation to the minds tracing arcs across the sky. When 3i Atlas disappeared behind the sun, the question of its path remained suspended in silence, waiting for December. Waiting for the moment when the object would re-emerge and reveal whether gravity alone had guided it, or whether something else, something unspoken, shaped the line it carved through space. And until that moment, scientists could only watch the empty sky and admit what few are willing to say. Sometimes the universe writes trajectories that feel like messages. Sometimes the improbable is simply the real. And sometimes the path of a visitor tells us not where it is going, but what we are ready to question. The approach of October gave the entire scientific community a feeling that is difficult to name. Not anxiety, not excitement, something quieter, something like standing at the edge of a long hallway, waiting for a door at the far end to open. The world knew that October 3rd would not bring disaster, only understanding. Yet even understanding can feel heavy when the universe has been whispering strange things for months. 3i Atlas would soon pass near Mars, close enough for orbiters to turn their cameras outward instead of downward. For the first time in human history, another planet would attempt to photograph a visitor from beyond the sun. The thought carried a quiet symbolism. After decades of sending machines across space, humanity had accidentally positioned them in just the right place to witness something extraordinary. The high-rise camera would not capture sharp details, only a faint separation between nucleus and halo, a silhouette amid dust, but even that would be enough. If the nucleus measured around 5 kilometers, the mass calculations would hold. If it appeared larger, the natural explanations would strain. If smaller, the mystery might soften, though only slightly. Size in this case was not just measurement, it was identity. Around Mars, other orbiters prepared their instruments as well. Mars Express, Trace Gas Orbiter, each one equipped with sensors designed for Martian geology and atmosphere, now repurposed to read the chemistry of a traveller passing millions of kilometers away. If there were fragments ahead of 3i Atlas, whether natural or not, these spacecraft might be the only eyes capable of seeing them. This possibility was rarely spoken aloud, but it hovered at the edge of every briefing. Even silence, when shared, becomes its own form of acknowledgement. The weeks leading to the flyby were shaped by another deeper issue. After passing Mars, the object would slip behind the sun, hidden for 2 months in the brightest blind spot in the sky. Its closest approach, its most intense heating, its greatest physical changes, all of them would unfold in a region no Earth-based telescope could penetrate. The universe had drawn a curtain at the exact moment when transparency was most needed. For a natural comet, this blackout was merely inconvenient. For anything else, it was a perfect shield. Behind the sun, 3i Atlas could fragment, adjust its course, slow down, accelerate, or shed mass in ways that would remain invisible. The sun would not simply illuminate the object, it would conceal it. And concealment, even accidental, always invites speculation. Still, scientists grounded themselves in evidence. They prepared predictions, calculated trajectories, and held fast to the expectation that natural forces would dominate. But at the edges of those expectations, questions accumulated like static. Why did this visitor align so precisely with the ecliptic? Why did it approach just as new observational instruments became available? Why did every anomaly seem to form a chain rather than a coincidence? These questions did not demand answers, but they made the waiting feel heavier. December 3rd became the next anchor in the collective imagination. That would be the moment of re-emergence when the object slipped out of the sun's glare and into the field of telescopes worldwide. Nearly every major observatory would be pointed at the region of sky where 3i Atlas was expected to reappear. Amateur astronomers prepared their equipment with unusual care, knowing that sometimes the first glimpse comes not from a billion-dollar facility, but from a small observatory on a quiet hill. The critical question was simple: would the trajectory match the predictions? If yes, the laws of gravity would hold their ground. If no, something else had acted upon it. Trajectory is the most honest evidence the universe gives us. Photons can mislead. Chemistry can confuse. Dust can disguise. But motion the arc through space reveals truth without intention or bias. A deviation of even a few arc seconds could redefine everything we thought we knew. Between October and December, Earth would be nearly blind. Only Mars orbiting spacecraft, distant probes, and partial detections would offer clues. The uncertainty itself became part of the story, a kind of cosmic intermission in which the universe held its breath alongside us. Meanwhile, private conversations began forming behind closed doors. Not public statements, not official protocols, just quiet discussions among scientists who understood what was at stake. What would happen if the trajectory shifted? What steps would be required to verify such an anomaly? How should the public be informed? What would constitute sufficient evidence? No one had answers. SETI had rules for radio signals, not physical visitors. Planetary defense protocols assumed rocks and rubble, not enigmas. Astronomy itself had no precedent for this moment. And yet beneath the uncertainty lay a deeper human truth we wanted to know. Even if the answers disrupted our assumptions, even if they complicated our models, even if they humbled us, some researchers proposed an intercept mission, a probe launched, quickly aimed to rendezvous with 3i Atlas before it drifted too far. It was an ambitious idea, almost desperate in timing. The window was brief. Even the fastest possible craft would take months to reach the object, and by then it might already be receding into the dark. But the proposal itself revealed something important. Humanity was unwilling to let this visitor pass without understanding it. As October 3rd drew closer, the world settled into a rare state of scientific anticipation. This was not the countdown to a launch, or the excitement before a discovery. It was a quiet readiness shaped by humility and curiosity. Whatever 3 Atlas revealed or refused to reveal would not change the universe, but it might change our understanding of it. The flyby would not resolve the mystery. It would only begin the verdict. And somewhere in the stillness of the night sky, with Mars preparing to cast its distant gaze on a stranger from the stars, the universe seemed to whisper the same reminder it always offers at such thresholds. Some mysteries do not arrive to frighten us. They arrive to measure the size of our wonder. There is a strange kind of quiet that settles over the scientific world when the instruments have done all they can, and the next piece of truth must come not from effort, but from waiting. After October 3rd, after the Mars orbiters completed their careful scans of 3 Atlas, the universe shifted into that quiet. A pause suspended between data and meaning. The object drifted on, curving toward the sun, and Earth could do nothing but watch the orbit line on a screen grow closer to the region of space where human sight fails. This was the beginning of the blackout, the long silence when 3i Atlas would be swallowed by solar glare. Astronomers knew this window was coming. They had calculated it, prepared for it, tried to work around it. But no preparation changed the comfortless truth. For 60 days, the most anomalous object ever observed would be hidden behind the sun, unreachable except by distant probes not designed to study it. To scientists, it felt like the universe closing its hand around a secret. For listeners and observers who followed the story from afar, the blackout carried a different emotional weight. It felt like losing track of a pulse they had just begun to hear. There is something ancient in human nature that fears losing sight of what we do not understand. Even now, in an age of probes and telescopes, that instinct surfaces the feeling that meaning might slip away when the sky goes silent. Before the blackout, the last images from Mars orbiters were analysed with almost meditative intensity. The high-res camera showed only a faint shape, a blur with hints of density near the core, but nothing decisive. The size estimates remained uncertain. No clear fragments ahead of the object were detected, though some scientists argued that detecting anything smaller than a large building at that distance was nearly impossible. The instruments captured what they could, and then the object drifted into the sun's blinding path, leaving behind partial truths that raised more questions than they settled. Traveller, this is often the rhythm of cosmic understanding clarity, followed by silence discovery, followed by waiting. The universe never reveals itself all at once. It arrives in moments and glimpses and echoes in data that glows faintly, and then disappears into the solar wind. It teaches patience by design. During the blackout, theoretical work intensified. Groups of researchers across observatories, universities, and small private labs ran simulations again and again, testing every plausible trajectory. They tried adjusting mass spin rate dust production outgassing patterns, but no model comfortably explained the object's extraordinary stability. Even with significant material loss, the orbit barely shifted. That alone was enough to disturb the deeply held assumptions of comet physics. Some scientists leaned toward natural explanations, invoking unusual compositions, ancient surface hardening, or unexpected internal cohesion. Others quietly admitted that the object behaved as though it possessed intentional stability, a trait more often associated with engineered systems than frozen ice. These conversations rarely reach public ears. Not because there was secrecy, but because scientists dislike speaking speculation into the air before evidence anchors it. And yet the questions lingered at the edges of every discussion. What if the silence behind the sun was not just geometry but timing? What if something natural or otherwise would change during the blackout? In the darkness of those 2 months, as the object curved toward perihelion imagination, filled the space where data could not reach. Some feared fragmentation. Others wondered whether 3i Atlas would survive its close kiss with solar radiation. Some entertained the possibility of course corrections, subtle shifts, visible only when the object re-emerged, and a few quietly and without fanfare wondered whether the object would reappear at all. Because sometimes traveller disappearing behind the sun is not just a blackout, it is a choice. Meanwhile, distant missions tried to help. SOHO watched its coronagraph for faint traces of movement. Parker Solar Probe attempted indirect reading through its instruments. Even Jupiter's JUICE spacecraft attempted to schedule opportunistic observations while using its antenna as a heat shield. But none of these were designed to study dim objects near the solar furnace. Their glimpses were fragments, noise, quiet variations, incomplete shadows. Nothing enough to replace true visibility. Earth for once was helpless. The world had grown used to the idea that nearly everything could be monitored. Storms, asteroids, flares, drifting satellites. But interstellar visitors do not obey our expectations. They move through our system like old memories slipping across a room, leaving no handhold for certainty. December 3rd became the horizon of hope. The date felt mythological, almost ceremonial, the morning when the object would emerge once more from behind the sun, returning, either unchanged, altered, or gone. Telescopes around the world prepared their schedules months in advance. Amateur astronomers calibrated their gear, knowing that sometimes the first detection comes not from billion-dollar instruments, but from a lone observer under a cold sky. The waiting period became an exercise in stillness, a reminder that cosmic time is indifferent to urgency. Some nights scientists stared at empty skyfields where 3i Atlas would soon emerge, feeling something they rarely admit: humility. In the great ledger of the universe, humanity is young. We are still learning the alphabet of the stars, and sometimes that learning requires accepting that the next page cannot be turned early. But the blackout also carried a softer truth. In the absence of observation, perspective deepens. Without new facts, the mind explores what it already knows with greater care. The anomaly of the nickel, the impossible mass, the absence of iron, the faint forward glow, the 1 in 500 orbit. All these pieces became clearer when seen together like constellations that reveal their shape only when you take a step back from the sky. Some mysteries sharpen in silence. As the days moved slowly toward December, one lesson became unmistakable. It is all right not to understand. The cosmos does not ask us for conclusions. It asks for wonder. Not certainty, but sincerity. Not answers, but attention. And so the world waited, as it always has, with questions held gently in both hands. Somewhere beyond the sun's blinding light, 3i Atlas continued its long silent trajectory. Whether it remained natural engineered or something between those categories did not matter in that moment. What mattered was that humanity was watching not with fear, but with a quiet readiness to learn. Because some mysteries are not meant to be solved quickly. Some must pass behind the sun before they reveal who they truly are. There are moments in astronomy when the flow of time seems to loosen, when days feel less like steps forward, and more like quiet repetitions of the same breath. The period when 3i Atlas moved behind the sun created exactly that sensation. It was as though the universe had paused its own clock, leaving humanity in the stillness between events, waiting for whatever came next. With the object hidden in solar glare, data streams went silent, and all that remained was the collective hum of anticipation. In that waiting, scientists revisited every anomaly with new intensity. The absence of iron, the dominance of carbon dioxide, the improbable stability of the orbit. Each detail became sharper in the quiet. The mind works differently when deprived of new information. It circles around what it already knows, polishing old observations until their edges gleam more clearly. That is what the blackout forced upon us, contemplation instead of action. Some researchers found comfort in the belief that natural explanations would eventually emerge. Comets, after all, often resist easy classification. Others felt that 3i Atlas had drifted too far outside the margins of known behaviour. Its mass, its chemistry, its geometry, every trait seemed to belong to a category that did not yet exist. And when science lacks categories, it expands them. The silence became an incubator for new possibilities. Meanwhile, people outside the scientific world drifted toward their own forms of reflection. Without telescope images or updated plots, the narrative became internal. Students watched simulations. Stargazers checked the skies where the object would eventually reappear. Online communities speculated and debated not out of fear, but out of curiosity. A global pause like this is rare, the entire planet waiting for the same event in the same month, listening to the same cosmic uncertainty. The blackout was not just an observational limitation, it became a shared emotional space. Even those who did not follow astronomy closely sensed that something meaningful was unfolding, not a crisis, but a conversation between humanity and the universe. It reminded us how small we are and how remarkable it is that we can even perceive mysteries like this. During those weeks, scientists ran simulation after simulation, tweaking parameters in search of a stable model. None fit perfectly. The object lost material but barely changed course. The chemistry seemed primordial, yet out of balance. The orbit hugged the ecliptic as if chosen. And though many resisted the idea, there was an undeniable elegance in the way each anomaly linked to the next. It felt intentional, even if intention was the last explanation anyone wanted to reach for. Still, curiosity is gentle, not reckless. It does not leap to conclusions. It simply walks toward them, slowly listening for inconsistencies along the way. As 3i Atlas curved deeper into the sun's gravitational well, no instrument recorded signs of catastrophic fragmentation. No unexpected bursts of light were seen in the solar-facing direction. Probes like Soho and Parker captured only faint noise, no dramatic plumes, no bright debris. That absence of violence was itself a form of information. Even near perihelion, the object behaved with a strange restraint. In the days leading to December, observatories began preparing for the moment of reappearance. Schedules were adjusted. Software pipelines were built for rapid detection. Amateur astronomers checked their tracking mounts, knowing that sometimes the universe rewards the patient outsider before the sophisticated institution. Everyone from quiet backyard skywatchers to multinational observatories was ready. And beneath all the preparation was something deeper: humility. Astronomers rarely speak of it openly, but moments like this bring it to the surface. The universe is vast, ancient, and impartial. It does not bend to human speed. It does not reveal itself on demand. When an interstellar object passes behind the sun, we wait. When it returns on cosmic time. This waiting created a kind of intimacy with the mystery. For once, there was nothing to analyze, nothing to measure, nothing to debate. Only the shared acknowledgement that something unknown was moving through our cosmic neighbourhood. Travellers on Earth looking up in the early morning cold felt closer to one another and closer to the sky. Perhaps this is the true gift of interstellar objects, not the data they deliver, but the perspective they restore. They remind us that we exist inside a much larger structure, one that operates without our permission yet invites our curiosity. They remind us that awe is a scientific tool too, that wonder sharpens perception as effectively as mathematics. As December drew near, the questions multiplied. Would the object reappear exactly where calculations predicted? Would its brightness change? Would its chemistry evolve after enduring the sun's heat? Would fragments accompany it? Would a deviation in trajectory expose an unseen force? These questions did not unsettle the scientific community. They energized it. Because at the heart of this mystery lies a simple truth: whatever 3i Atlas is, it has already changed us. Even before emerging from behind the sun, it expanded the boundaries of what we consider plausible. It forced us to think in terms of billions of years, interstellar chemistry, and unexpected geometry. It encouraged us to embrace ignorance as a temporary form of clarity. Standing beneath the night sky, people across the world waited not for certainty but for revelation. Something would appear in December, something that had crossed light years to meet us. Whether it returned unchanged, transformed, or fragmented, it would carry new information. It would speak the next sentence in a conversation humanity did not know it was having. This is the quiet truth the universe often teaches. You do not need to understand everything to feel a connection to it. You only need to remain open. And so the world waited in observatories and quiet homes in open fields under cold skies, ready to greet whatever stepped out of the sun's shadow. When 3i Atlas re-emerged, it would either confirm our models or expand them. It would either return predictably or surprise us again. In either case, it would belong to the same cosmic story we have been trying to read for centuries. A story written in dust, gravity, silence, and light. Traveller, our journey settles into its final breath tonight. We have drifted together beside 3i Atlas through its strange chemistry, its impossible trajectory, and its quiet defiance of everything we thought we understood. Now it slips behind the sun, entering a place where our instruments fall silent, as though it is turning a cosmic page we are not yet ready to read. In the hours ahead, astronomers will chase certainty, pointing cameras and equations toward the unknown, hoping the universe will speak in numbers they can hold. But you listener have taken a rarer path. You paused, you listened, you allowed the mystery to exist without demanding that it resolve. And that gentle act of witnessing is its own kind of knowledge, its own kind of belonging. The cosmos is not a puzzle to be conquered, it is a presence to sit with a silence that invites humility. Whatever 3i Atlas becomes in the days ahead, ordinary, extraordinary, or something that refuses both categories, it already leaves us with a truth older than starlight. We are small, yes, but we are never insignificant. To look up is to participate. To wonder is to join the long lineage of observers who have learned to live with the unknown. Somewhere beyond the solar glare, the object continues its slow, deliberate arc, carrying its secret through windfire and darkness, and the universe whispers again, some mysteries aren't meant to be solved, only observed. So rest now, traveller. Let the unanswered drift gently across your thoughts. Stay curious. Rest well. The universe will keep watch.